In the next few slides, we will continue to examine the problem of ax equals to b, and our problem again is find the x such that ax is produced to be nearest to b. This is the space of x. It is Rn because A is Rm by n. Ax, therefore x is of dimension n. Among any x that we can take in this space, we are interested in the x hat such that when x hat is multiplied on the left by A, it will produce b hat, and b hat is in the column space of A such that the error is orthogonal to the column space of A. In the last lecture, we have seen two ways to solve this problem. On the left, we have used calculus to solve it. And on the right, we have used brute force to solve it. In today's lecture, we are going to use the linear algebra's approach, which is to form the normal equation. The normal equation is formed by multiplying the left-hand side by A transpose, and hence the right-hand side we will also have to multiply by A transpose. We'll get this equation called A transpose AX equals to A transpose B. This is the normal equation. The least squares solution of x can be found from this normal equation. How do we prove the normal equation? We'll use first this figure. This is the desired point B in the space of Rm. B hat is equals to Ax hat. We do not know the value of Ax hat now, but what we know is that for the error to be smallest, the error vector E equals to B minus B hat must be orthogonal to the column space of A. The column space of A means any vectors made up by columns of A linear combinations. There is any linear combinations of columns of A. In other words, the error vector E is orthogonal to all columns, each and every column of A. Therefore, if Aj is A1, A2, An, where this is the matrix A, Aj is each one of the column of J. J is equals to 1 to N, any of the columns of A. It is orthogonal to the error vector. That means the dot product of the columns, any of the columns of A, is orthogonal to the error vector B minus Ax hat. The dot product can be represented in another way using vector to vector multiplication. What we do is that we turn the column vector into a row vector by saying Aj transpose, and then we are multiplying with the column vector B minus Ax hat. Now Aj, J is equals to 1 to N, means that all the rows need to satisfy this criteria, we can actually combine all these rows into the matrix A transpose. This basically have A1, A2 transpose until AN transpose, implying that this equation says that all columns of A is orthogonal to the error vector, which is exactly this diagram here. The error vector is orthogonal to any vectors in the columns of A. We are almost in a position to see the normal equation. All we need to do is to expand this equation by removing the brackets. ATB minus ATAX hat equals to 0. We can now move one of the part of the equations to the other side, which gives us ATAX hat equals to ATB. These few steps shows that the least square solution for AX equals to B will satisfy this equation. This equation is called the normal equation. Have a look at Wolfram Math World. Under the normal equation, it says that the normal equation is called normal because the error vector B minus AX is normal to the range of A, that is the column space of A. Now, why are we almost ready to solve for X? Because if A is a matrix of M by N, A transpose is a matrix of N by M. A transpose A is a matrix of N by M multiplied by M by N, thus dimension agrees, will produce a square matrix of N by N. This being a square matrix, if its inverse exists, ATA inverse, if it exists, then we can multiply this equation, the normal equation, by ATA inverse on the left hand side, means that we also multiply on the right hand side, we'll get this equation. ATA X equals to ATA inverse ATB. Remember that if by multiplying on the inverse of the matrix, we get identity, which is this equation here. We'll strike off, reducing it to I, implying X is equals to ATA inverse multiplied by A transpose B. So basically, if we have ATA being invertible, we can get X hat in this form. Getting X hat in this form is the least square solution of X. The X that will produce the least error, the least squares error. Now, in most cases, ATA is invertible. When ATA is invertible, these three conditions are logically equivalent. It means that the columns of A are independent. It means that the solution of AX equals to B is unique. In the next 3 slides, we have some examples.